of summer talks. Today I'll be presenting on my closed loop insulin pump that I've created the past 8 weeks. So I guess I should start with my motivation behind this project. It started 18 years ago whenever I was diagnosed with type 1 diabetes. Actually, whenever I was 2 years old, I was the youngest person in the state of Texas to wear an insulin pump. So I guess you could say that this is in my blood, both literally and figuratively. So another thing that I wanted to address in my presentation or in my project was cost. The MiniMed 670G hybrid closed loop system, which is a hybrid closed loop system, something similar to what I'm making, costs around $10,000. I know for a lot of people that's out of most budgets, so I'm trying to address that. Also, this system is a hybrid closed loop system. It's not truly closed loop. It requires user input, so I'm trying to address that as well. And also, current biotechnology in the diabetes field is not very reliable. I know in the past 6 months alone, my insulin pump has failed 3 times, and for something that your life depends on, I don't think that that is acceptable, and so that's another thing that I'm addressing. I should start by defining what exactly a closed loop system is, and it's defined as an automatic control system in which an operation, process, or mechanism is regulated by feedback. And what this means in terms of an insulin pump is your blood sugar, which is your feedback, and the insulin pump is the operation, and so they control each other and create a loop and requires no user input. Like I said before, this is the MiniMed 670G. It's over $10,000, and this closed loop system has already been created, but there are some major issues that I'm addressing in my project, which I will get to. So these are some of the components that I'm using for my project. I realize that some of this is a lot of jargon, but I will get to it later in the project, I promise. So I'm using a continuous glucose monitor. This is just a device that I wear that reads your blood sugar every 5 minutes. And it's what I use to run my Night Scout app, which I will get to in the next couple slides. A database to hold all my information. I'm using a Raspberry Pi, as well as 3D printing all of the physical components. So first I should start with the app. This is really the basis of the project. I had to deploy this app, and it's kind of like the control center for my data path. You can see in the bottom left corner there is the start of a flowchart, and that will kind of keep track of the complex data path so that it's easier to follow. And this is actually a live reading of my blood sugar right now. So it's connecting through this HTC phone and updating continuously. So I have constant record of my blood sugar. Next, I used a Mongo database. What a database is it's just a container that holds all of your information. And the app sends data straight sends blood sugar data, pump data, and where your blood sugar is trending, up or down. And that all that information is taken into account whenever my insulin pump that I've created is actually inducing insulin. Okay, so the next component is the microcontroller, and I'm sure a lot of you are probably wondering what that is, because at the beginning of the summer I had no idea what it was. What this is basically just a mini computer. It allows you to control certain hardware. You can see these pins going up the right side of the Raspberry Pi. You can connect different devices and control them. I'm controlling a stepper motor. This is what a stepper motor is. It allows you to program and turn it a certain number of degrees or steps, and that allows you to control how much insulin you're actually pumping. And the Raspberry Pi controls that. Also, I have my program which pulls the data, and it also is able to connect to the database that has all of my information in it. So I decided to use Python as the language of choice for this project because there is an interface called PyMongo, which allows your Python program to directly connect to your database, and it makes it very easy to pull information like blood sugar values, where it's trending, and make decisions off of that. And onto some of the physical components. You might be wondering why I decided to use 3D printing. There's a couple reasons. First, it addresses my main issue with cost. You can get a very good 3D printer nowadays for as little as $200. I actually ended up buying my own through this project. And filament lasts forever, and you can get an entire 1 kilogram spool for as little as $20. So I could probably make 200 iterations of my pump with 1 spool of filament, and that makes it very, very cheap. Also, it's something that I've always wanted to get into, but I didn't have the means of actually getting a 3D printer and educating myself, and being exposed to it in the DTSF program really helped and kickstarted that. So that's another reason behind why I chose 3D printing. So this is a 3D design software. It's called Tinkercad. I also used another one called Fusion 360. All you need to know with this is that there are a bunch of simple shapes that you can create more complex objects with. This is actually my 3D design for my insulin pump. And that's what I used to design my insulin pump. Here's the physical insulin pump. As you can see, the Raspberry Pi and the stepper motor driver is all connected in the case on the left. Here is the stepper motor that I showed you, as well as a gear series. I'm using a rack and pinion gear series, which I can show you right here. So this is 250% scale of my actual insulin pump. So the stepper motor will go on right here. I didn't happen to have one large enough to fit this. So it will turn this gear, and this is connected to the plunger on the syringe, and it inputs a certain amount of insulin. And that's basically what a rack and pinion gear setup is. So everything, the physical gears, all of the components, and the case for the pump, they were all 3D printed. It probably costs less than $2 to do it all. As I mentioned, the stepper motor and gears pump the insulin, and the Python program controls the stepper motor. As you can see by the flowchart at the bottom, we are now getting into the physical insulin pumping side of things with the program controlling the insulin pump. And that closes the loop. So we start with data from the CGM. It's constantly taking a poll of my blood sugar every 5 minutes and updating it into the Night Scout app. Then the Night Scout app is sending it to my database. And then PyMongo pulls data from the database, and the program uses that information to correct my blood sugar. And every 5 minutes, that is a loop, and it keeps constant account of your blood sugar and constantly correcting it. So it is a true closed loop system. And so back to my main issue with cost. So to start out, the Raspberry Pi is an entire computer for only $35, which is kind of amazing. All of the cables were less than $10. I was generous with that, as well as the motor and accessories. You can really get one of these motors and its driver for about $1. So I just put down 5 because we actually used 5 of them to find one that worked. And also the printer and filament. The printer, I actually bought my own, so I added that into the cost. So that was only $210 for that entire setup, as well as the continuous glucose monitor that I'm wearing, and that's the most expensive piece at $500. I used a recycled HTC smartphone, not an LG smartphone, which I showed you here, with a meter that I already had to upload all of my data. And the total cost of that adds up to $730. And if you compare that to MiniMed's hybrid closed loop system, which isn't even a true closed loop system, it comes in at $10,000, making a huge difference of $9,270. So some of the things that I've accomplished over this summer, I actually have working prototypes. I can show you now that this actually does run and work. And you should see, I'm using water, but it actually does run. It does work. That's a little bit exaggerated. That would probably kill someone, but just for presentation purposes, so that you guys can see, I have that there. Also, my app was successfully deployed. That was probably the biggest headache ever. But with some other programs, it wasn't too difficult. The stepper motors are all correctly configured, and as you saw, it works. Cost was greatly reduced by over $9,000, which is a huge win in my head, as well as a truly closed-loop system. I think I read somewhere that only 56 other people in the entire world have done this, and I like to think that I'm the first solo college student that has ever done this, from scratch also. And then where do I go from here? So insulin calibration is the first and probably most important thing. Each person responds to insulin in different ways. So creating something like a graphical user interface, which can allow people to input their own settings that they're familiar with, can help with getting them the right amount of insulin at the right time and keeping their blood sugar as stable as possible. Also, this design works pretty well, but some more design iterations can help make it more reliable. As you can see, these are all design iterations that did not work. And so with 3D printing, it has allowed me to do it cheap, and within a few hours you have an entirely new design that may or may not work. And then making it more portable. As you can see, this is kind of a mess and pretty large compared to the MiniMed 670G. I'm actually wearing it right now. This is the size of that compared to this, but with smaller components, it's definitely possible to make it smaller. And that comes with reducing size and making it more portable. So I'd like to thank everyone, Dr. Ramey, and then the IT department, as well as Eric. I don't know if he's here, but he helped me with some major networking problems, as well as everybody else who has supported me in this project. So thank you.